Hello everybody, get ready to do lesson 7.3 part 2 of classwork of pre-calculus math today. And today we got 10 points here to go. We'll go into your notebook for 7.3 part 2, multivariable linear systems. And then we have a 36-point classwork sheet today. And today's bell work, students, teachers, write the expression as the logarithm of a single quantity here. Log the expression as a single logarithmic quantity down here. Give your students 5 minutes, teachers, turn off the video, and see you in 5 minutes. Okay, welcome back everybody for your solutions for today's bell work. 2 natural log x minus natural log of x plus 2. How do we write this expression as the logarithm of a single equantity? The key is this subtraction sign. So what does that mean in logarithmic quantities? It means, well, we have a quotient here. The natural log of x squared minus natural log of x plus 2. That would be this as a single quantity, a simplified quantity. And then for this one down here again, we have another subtraction sign. So 1/2 natural log x quantity x squared plus 4 minus natural log x equals natural log of x squared plus 4 to the 1/2 power minus natural log x. And then this becomes, we factor out a natural log here, and we have x plus 4 to the 1/2, which is radical x plus 4, divided by natural log x, which is a quotient down here. So this will be our simplified expression for this. Okay, moving on into our lesson today. As with a system of linear equations in 2 variables, the number of solutions of a system of linear equations in more than 2 variables must fall into one of 3 categories. The number of solutions of a linear system. For a system of linear equations, exactly one of the following is true. 1, there is exactly one solution. 2, there are infinitely many solutions, number of solutions of a linear system. Or 3, there is no solution. So these are your 3 possibilities here. Page 2 of your notebook. A system of linear equations is called consistent when it has at least one solution. A consistent system with exactly one solution is independent. A consistent system with infinitely many solutions is dependent. A system of linear equations is called inconsistent when it has no solution. So we have independent, dependent, and inconsistent and consistent. So we have 4 different terms there to be prepared to know. So let's try one now. Let's try a system with infinitely many solutions. Solve the system of linear equations. So we have equation 1, 2, and 3. Here's our system. So we're going to add the first equation to the third equation, produces a new third equation. Here's our new third. We got rid of our x here. These canceled each other out. Now we're going to add -3 times the second, -3 times our second here to the third equation, produces a new third equation. So now when we do that, we have 0 equals 0 now is what we have. So, well, I guess okay, so far. This result means that equation 3 depends on equations 1 and 2. In that sense, it gives no additional information about the variables. So the original system is equivalent to x plus y minus 3z equals -1, y minus z equals 0. So this should be our original system here instead of starting with the 3 equations. So in the last equation, solve for y in terms of z to obtain y equals z. Back substituting for y in the previous equation produces x equals 2z minus 1 for this situation up here. If y equals z, then x will equal 2z minus 1. Knowing that, finally letting z equals a, where a is a real number, the solutions of the original system are all of the form x equals 2a minus 1, y would equal a, and z would equal a. So every ordered triple of the form 2a minus 1, a and a, where a is a real number, is a solution of the system. So this is an algebraic representation of the ordered triple for that solution. So let's try one now. Solve the system of linear equations and check any solution algebraically. Here's our system here. Equation 1, 2, and 3. So we're going to multiply equation 1 here by 1/3. And we get this now for equation 1. Then when we get that, this changes our system to this now. Then we have -1 times equation 1 plus equation 2 will give us this here, 3y minus 3z equals 3. And then -5 times equation 1 plus equation 3 will give us this new manifestation for row 3, or equation 3, -3y plus 3z equals -3. When we do that, what do we have next now for that? We end up with this here, 0 equals 0, then x minus y plus 2z equals 2, y minus z equals 1. And so now we can go down further here, x plus z will equal 3 here. And then y minus z will equal 1 here. Let's see here. Let z equal a, then y would equal a plus 1, then x would equal -a plus 3. So we have x here, we have y, and then we have z here. So knowing that, here is our ordered triple for that system. It would be -a plus 3 for x, and then y would equal a plus 1, and then z would equal a from this manifestation here. In example 4, there are other ways to write the same infinite set of solutions. For instance, the solutions could have been written as b 1/2 times quantity b plus 1, 1/2 b plus 1, where b is a real number. This description produces the same set of solutions as shown below. So, okay, let's get into a table here. When a equals 0, so 2 times 0 minus 1 would give us 2 times 0 minus 1, and then 0, 0 will give us -1 and 0, 0. That would be one possible solution for that. And then when b equals -1, we get this as our ordered triple now, -1, 0, 0. When we plug that into our formula up here, same solution. Notice -1, 0, 0, 0. When it's 0 and then -1, we get the same solution here. And then when a equals 1, we have this different kind of product here will give us 1, 1, and 1 as our ordered triple. And then when b equals 1, we get the same solution here as well. So this is the same solution as well. Okay, continuing on with our table here displaying these kinds of solutions. So when a equals 2, we get 3, 2, and 2 as our ordered triple. And then when b equals 3, we get the same thing here, 3, 2, and 2 with that previous system. Then when a equals 3, when we plug that into our formula here to find our ordered triple, we have 5, 3, and 3 when a equals 3. And then when b equals 5, we get the same solution again. So we come up with infinite amount of solutions with a system like that. Let's go into non-square systems now, covering non-square systems. So far, each system of linear equations you have looked at have been square, which means that the number of equations is equal to the number of variables. In a non-square system of equations, the number of equations differs from the number of variables. A system of linear equations cannot have a unique solution unless there are at least as many equations as there are variables in the system. Now that's a very interesting factoid there. A system of fewer equations than variables. Solve the system of linear equations. So we have 3 variables here with 2 equations. Equation 1, equation 2. Begin by rewriting the system in row echelon form. So when we do that, we can get this by adding -2 times the first equation to the second equation produces a new second equation. Here's our new second equation. Multiplying the second equation by 1/3 produces a new second equation. Here's our new second equation after we do this step. Okay, so moving right along now into page 11, and solve for y in terms of z to obtain y equals z minus 1. So this would be our second row here. We have this quantity here for y. By back substituting into equation 1, you can solve for x as follows. So we know what y is. So we back substitute into equation 1. We get x minus 2 times quantity z minus 1 plus z equals 2. And then we end up with this here, this expression here after we do our distributive property of multiplication. So when we solve for x, we end up with x equals z for x. This is what this will end up down here. When we have that, finally by letting z equals a, where a is a real number, you have the solution here of x equals a, y equals a minus 1, and z equals a. So for every order triple of the form a minus 1, and a, where a is a real number, this will be a solution for that system. Okay, so let's try one here. Solve the system, linear equation, check any solution algebraically. So we don't have a 3 by 3, we got a 3 by 2 here basically. So we have equation 1, equation 2, and then our equation 1 here is that, and then our equation 2 can be changed by -4 times equation 1 plus equation 2. So when we multiply -4 times equation 1 plus equation 2, we get this down here. We get rid of our x, and we end up with 8y minus 21z minus 8. So when we have that, when we multiply equation 2 now by 1 over 8, this will just give us a y here. We'll end up with this fraction here, -21 over 8 for z, and then we have -1 out here. Then we can multiply 2 times equation 2, 2 times equation 2 plus equation 1. So 2 times equation 2 plus equation 1 2 times equation 2, so this will go away here, and we end up with x minus 1 over 4z equals 0. That'll go away too. And then we end up down here for equation 2 will be y minus 21 over 8z will equal -1. So what do we do with that? So let z equals a. We're going to let z equals a. Then y will equal 21/8 a minus 1. And then x will equal 1/4 a. So here's our ordered triple for this system here. 1/4 A, 21/8, A minus 1, and then A for that. So let's get a table going. In example 5, try choosing some values of A to obtain different solutions of the system, such as 101, 212, 323. Then check each of the solutions in the original system as follows. So we're going to check 101 for example 5. And when we do that, when we plug these values in, we get 2 equals 2. So that does check. And then we can go again 2 times 1 here, 2 times 1, and minus 0, minus 1. Will that be a consistent system? It is. 1 equals 1, so that works as well. So now we're going to check 212 in our example 5, 212. And then when we do that, we 2 minus 2 times 1 plus 2, and that shows that it is valid. And then for 2 times 2 out here, we've already see 2 times 2 minus 1 minus 2 equals 1. It does. So that solution is valid as well. And then I'm going to check 323 for our to see if it is a valid solution for that. 3 minus 2 times 2 plus 3 equals 2, and it does check out. And then 2 times 3 minus 2 minus 3, does that equal 1? And it does equal 1. So our solution does seem to be valid for that situation. That's your 7.3 classwork 7.3 part 2. And here's my email if you need solution PowerPoints or any other course materials, classwork sheets, homework sheets, notebook guides. Email me here. Thank you very much.